October 10th, 2025. While every telescope, headline and late-night podcast obsesses over 3i Atlas brushing past Mars, something stranger is unfolding much closer to home. A comet, faint and overlooked, is on course to skim by Earth in just 10 days. It wasn't spotted until after it had already looped around the Sun. Imagine that, a celestial visitor slipping past our defences, silent until it was almost here. Tonight, we peel back the curtain on why 3i Atlas isn't the story, but why this lesser-known object might be. Stay with me until the end, because the quiet threat we've ignored could change how we think about planetary safety forever. If this mystery has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these celestial visitors. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. Opening the Hidden Threat. While all eyes are on 3i Atlas and its Mars flyby, a different visitor, one we only discovered after it passed the Sun, is sliding closer toward Earth, and no one's sounding the alarm. You've probably heard the name 3i Atlas by now. The media loves a good space rock story, especially when it's exotic, potentially interstellar, and making a scenic tour past Mars. The headlines write themselves. Scientists are excited. Amateurs are pointing telescopes skyward. Social media is buzzing with speculation about where it came from, what secrets it might hold, whether it's natural or something else entirely. It's the perfect celestial distraction, the kind of cosmic event that makes us feel like we're paying attention to the universe's grand theatre. But here's the thing about theatre. While you're watching the main act, you might miss what's happening in the wings. On September 11th, 2025, a Ukrainian astronomer named Vladimir Bezugli was doing something most people don't even know is possible. He was looking at the Sun. Not directly, obviously, but through a specialized instrument aboard a satellite called SOHO, the Solar and Heliospheric Observatory. This instrument, called SWAN, for solar wind anisotropies, doesn't see visible light. It sees hydrogen. Specifically, it detects the glow of hydrogen atoms in the Lyman alpha wavelength, a signature that becomes visible when comets get close to the Sun and start to cook. Bezugli found something. A comet. Not a little one, not a faint smudge that would burn out harmlessly. A comet that had already passed perihelion, its closest approach to the Sun, just 1 day earlier on September 12th, at about 0.5 astronomical units. That's roughly half the distance from Earth to the Sun. The comet had survived its solar encounter, and now it was heading outward. Heading, as orbital mechanics would soon reveal, toward us. The object was designated C/2025 R2 SWAN. Let's call it R2 SWAN for simplicity. And here's where your attention should snap into focus. R2, SWAN's projected closest approach to Earth, is October 20th, 2025. That's right around now, depending on when you're hearing this. The distance? 0.26065 astronomical units. In human terms, that's about 38.99 million kilometers, or roughly 24.2 million miles. Now, before you start building a bunker, let me be clear. That's not an impact trajectory. Earth is not in immediate danger from a direct collision with this comet's nucleus. But let's put that distance in perspective. The Moon orbits Earth at about 0.00257 astronomical units. So R2 SWAN is passing us at roughly 100 times the Moon's distance. In cosmic terms, that's uncomfortably close. Close enough that if something goes wrong, if the comet fragments, if its trajectory shifts unexpectedly, we'd have very little time to react. And here's the part that should make you pause. We didn't see this thing coming. We only found it after it had already rounded the Sun, after it had already committed to its path through the inner solar system. The minimum orbit intersection distance, the MOID, the closest point where Earth's orbit and the comet's orbit come near each other in three-dimensional space, is about 0.048 astronomical units. That's roughly 7 million kilometers. In astronomical terms, that's a whisker. That's a rounding error. That's the difference between a footnote in history and a catastrophe. You might be thinking, okay, but we found it, right? We're tracking it now. The system works. Except the system didn't work. The system got lucky. R2 SWAN was discovered by an instrument that wasn't designed for planetary defense, by a person who happened to be looking at the right dataset at the right time, using a detection method that relies on the comet being active enough to produce hydrogen emissions. If this comet had been less active, if it had passed the Sun without warming up enough to outgas significantly, if Berzugli had been looking at a different patch of sky that day, we might not have found it at all until it was already past Earth. And that's the nightmare scenario that keeps planetary defense scientists awake at night. Not the big, obvious threats that we can see coming years in advance, but the small, sneaky ones that slip through the gaps in our detection grid. The ones that approach from the direction of the Sun, where our telescopes are effectively blind. The ones that don't reflect much visible light until they're already on top of us. The ones that we only notice when they start to fall apart. 3i Atlas is getting all the press because it's interesting, because it might be interstellar, because it gives us a chance to study something unusual. But R2 SWAN is the real story. It's the object that reveals how fragile our early warning system actually is. It's the canary in the coal mine, except the canary already flew through the mine and we only noticed it on the way out. So while everyone's talking about the visitor we saw coming, I'm going to tell you about the one we didn't. And more importantly, I'm going to show you exactly why that should terrify you. Not because of this specific comet, but because of what it reveals about the next one, the one we might not catch in time at all. In the next part, I'll show you exactly how it slipped by us, and why our telescopes were blind to it until it was too late. Part 2. How we actually found R2 SWAN. The comet didn't announce itself in visible light. It was lurking in hydrogen glow, only catching attention when it warmed and started emitting. You need to understand something fundamental about how we find things in space. Most of our detection systems, the vast majority of telescopes and surveys that scan the sky every night, work on a simple principle. They look for reflected sunlight. An asteroid or comet is essentially a dark rock or dirty snowball drifting through space. It doesn't generate its own light. It only becomes visible when sunlight bounces off its surface and travels back to our cameras. The brighter the object or the closer it is to the Sun, the more light it reflects, and the easier it is to spot. This works beautifully for most scenarios. We've catalogued hundreds of thousands of asteroids this way. We've found comets years before they reach their peak brightness. We've built an entire infrastructure around this method, and it's saved us from countless potential impacts. But it has a fatal flaw. If an object is positioned between Earth and the Sun, or very close to that line of sight, we can't see it. The Sun's glare overwhelms everything. It's like trying to spot a firefly hovering in front of a searchlight. The firefly is there, but good luck finding it. R2 SWAN approached from exactly this blind spot. During its inbound journey toward perihelion, it was hidden behind the solar glare for weeks, possibly months. Ground-based telescopes couldn't see it. Space-based telescopes that look outward from Earth's orbit couldn't see it. It was invisible, not because it was too small or too dark, but because it was in the one direction we can't safely point our instruments. This is where SWAN comes in, and why its existence is basically a happy accident for planetary defense. SWAN wasn't designed to find comets. It was built to study the solar wind, the stream of charged particles that flows outward from the Sun and shapes the space weather environment around Earth. The instrument detects hydrogen atoms in the solar system by measuring Lyman alpha emissions, a specific ultraviolet wavelength that hydrogen produces when it's excited by solar radiation. Comets, when they get close to the Sun, start to sublimate. Ice turns directly into gas, skipping the liquid phase entirely. Water ice breaks down into hydrogen and oxygen. The hydrogen forms a massive invisible cloud around the comet's nucleus, sometimes millions of kilometers across. This cloud glows in Lyman alpha, and SWAN, pointing toward the Sun to study the solar wind, happens to see it. Vladimir Berzugli was scanning SWAN imagery on September 11th when he noticed something unusual. A bright spot moving against the background. Not a star, not noise, a comet. He reported it immediately, and within hours the astronomical community started paying attention. But here's the timeline you need to appreciate. The comet had already passed perihelion on September 12th. It was on its way out. We didn't catch it on approach. We caught it on departure. A few days after Berzugli's discovery, ground-based observers started picking up R2 SWAN, invisible light and CCD imagery. By then, it had moved far enough from the Sun's glare that conventional telescopes could actually point at it without risking damage. Orbital elements were calculated, brightness estimates were refined. Updates flowed through the Central Bureau for Astronomical Telegrams and other alert networks. The machine of science kicked into gear, doing what it does best, analysing, predicting, communicating. But think about what this means. If R2 SWAN had been less active, if it had contained less water ice, or had a thicker dust mantle insulating its surface, it might not have produced enough hydrogen emissions to trigger SWAN's detection threshold. If its orbit had been slightly different, bringing it through perihelion at a different angle, it might have stayed hidden longer. If Bazugli had been on vacation that week, someone else might have noticed it days later, or not at all. We got lucky. That's the uncomfortable truth. Our detection of R2 SWAN wasn't the result of a robust, multi-layered surveillance system designed to catch every threat. It was the result of one instrument, built for a different purpose, happening to be in the right place at the right time, and one skilled observer recognizing what he was seeing. Now you might wonder, don't we have other systems for this? What about infrared surveys? NASA's NEOWISE mission, for example, detects asteroids and comets by their heat signatures. Infrared can penetrate dust and spot objects that are too dark to see in visible light. And yes, NEOWISE has been incredibly valuable, but it has limitations too. It scans the sky in specific patterns, not continuously. It's more sensitive to larger objects with stronger thermal signatures, and crucially it also struggles with objects close to the Sun, because the Sun's infrared emission overwhelms the detectors just like visible light does. What we need, and what we don't really have yet, is a complementary network. Multiple types of sensors, looking in multiple wavelengths, covering the sky from multiple angles, integrated into a single alert system. We need hydrogen and ultraviolet detectors like SWAN, but purpose-built for comet detection and positioned to maximize solar coverage. We need infrared surveys with better cadence and sensitivity. We need ground-based optical telescopes in both hemispheres with overlapping fields of view. And we need all of these systems talking to each other in real time, sharing data, cross-referencing detections, filtering false positives. The southern hemisphere is particularly under-monitored. Most major observatories are in the northern hemisphere, for historical and geographical reasons. An object approaching from the south celestial pole has a better chance of slipping through unnoticed. Add in the solar exclusion zone, the cone of sky around the Sun that we can't observe safely, and you've got a detection grid with holes big enough to drive a comet through. R2 SWAN threaded one of those holes. It came in from a southern trajectory, hidden in solar glare, producing just enough hydrogen emission at just the right time to ping SWAN's detectors. Any one variable different, and we might still be oblivious. Next, we'll talk about how R2 SWAN is behaving right now. Flares, green glows, and stray jets that might push it off course, because the story doesn't end with detection. It gets stranger. Part 3, real-time behaviour, outbursts, green coma, and unstable forces. The comet is alive, or at least volatile, and its behaviour is shifting under our eyes. That matters, because every jet or flare tweaks its path. Comets are not inert rocks. They're more like bottles of champagne under pressure, waiting for the right temperature to pop the cork. When R2 SWAN rounded the Sun and began its outbound journey, it started doing what all active comets do. It began to change. Observers around the world, both professional and amateur, started reporting unusual features. A green coma, that's the fuzzy cloud of gas and dust surrounding the nucleus, became visible. The colour comes from diatomic carbon and cyanogen molecules, fluorescent green when excited by ultraviolet sunlight. It's beautiful, almost alien, like something out of a science fiction film. But beauty can be deceiving. That green glow is evidence of intense chemical activity. The nucleus, probably just a few kilometers across, is shedding material at a furious rate. Gas jets are erupting from its surface, powered by sublimating ice. Dust particles, some microscopic, some as large as gravel, are being thrown into space. The coma and tail show structure, asymmetry, curvature. These aren't uniform, smooth features. They're chaotic, unpredictable, shaped by the rotation of the nucleus and the uneven distribution of volatile ices beneath the surface. In late September, R2 SWAN exhibited an outburst, a sudden brightening that caught observers off guard. Its magnitude, a measure of brightness, jumped significantly, possibly reaching as bright as 5th or 6th magnitude under favourable conditions. That's on the edge of naked eye visibility from a dark sky site. For a comet discovered just weeks earlier, that's dramatic. Outbursts like this suggest that a pocket of highly volatile material, maybe carbon monoxide ice or some other exotic compound, suddenly became exposed to sunlight and vaporized explosively. Here's why this matters for more than just pretty pictures. Every jet of gas or dust that erupts from a comet's nucleus acts like a tiny rocket engine. It imparts a force, a push, in the opposite direction. These are called non-gravitational forces, and they're the bane of orbital calculators. When you're trying to predict where a comet will be weeks or months from now, you need to account for gravity from the sun, planets, and moons. But you also need to account for these little kicks from outgassing, and unlike gravity, which follows precise mathematical laws, outgassing is chaotic and unpredictable. A comet with a short observational arc, meaning we've only been tracking it for a brief period, is especially vulnerable to trajectory errors. Small non-gravitational accelerations, if not properly modelled, can compound over time. They can shift the comet's closest approach distance. They can change its arrival time. In extreme cases, they can turn a safe flyby into a collision course or vice versa. We've seen this happen before. Comets have surprised us by arriving early, or by fragmentation events that scatter debris across a wider path than predicted. R2. SWAN's orbit right now is based on observations spanning just over a month. That's not a lot of data. Every new observation refines the trajectory, but also introduces new uncertainties as we try to model the outgassing forces. The transverse acceleration, the component of force perpendicular to the comet's direction of motion, is particularly tricky. It directly affects orbital parameters like eccentricity and perihelion distance. Even a small error in estimating this force can propagate into significant position errors by the time the comet reaches Earth's vicinity. And then there's the fragmentation question. Comets are fragile. They're not solid rock. They're more like loosely bound rubble piles held together by ice and gravity. Thermal stress from the sun can crack them. Rotational forces can tear them apart. Volatile pockets can explode and blow chunks off the nucleus. Comet Shoemaker Levy 9 famously broke into more than 20 fragments before slamming into Jupiter in 1994. Comet 73P Schwassmann-Wachmann has split multiple times, creating a family of smaller comets on similar orbits. If R2 SWAN were to fragment, we wouldn't be dealing with one object anymore. We'd be tracking dozens, maybe hundreds, each on slightly different trajectories. Some fragments might miss Earth entirely, others might come closer. The debris field would spread along the comet's orbit, creating a gauntlet that Earth would have to pass through. And because comets shed dust and gas continuously, even without fragmentation, there's always a debris trail extending along their path. If Earth's orbit intersects that trail, we could see meteor showers, or in a worst-case scenario, a barrage of larger particles capable of damaging satellites or spacecraft. The comet's activity also complicates impact risk assessment. When planetary defense teams calculate collision probabilities, they assume a single, solid object with a predictable orbit. But an active comet violates both assumptions. It's not a single object, it's a nucleus plus a coma plus a tail plus shed fragments. And its orbit isn't predictable with the same precision as an inert asteroid. Every outburst, every jet, every fragment that breaks off introduces new variables. So when you hear that R2 SWAN's closest approach is predicted for October 20th, at 0.26 astronomical units, understand that prediction comes with error bars. The comet could arrive earlier or later, it could be slightly closer or slightly farther, and if it's actively disintegrating as it approaches, the threat profile changes entirely. We're not just worried about a single impact point, we're worried about a cloud of debris smeared across millions of kilometers. This is the reality of dealing with comets. They're dynamic, evolving, messy. They don't follow neat deterministic paths like asteroids do. They're governed by physics, yes, but also by chemistry, thermodynamics, and sheer chaos. Every observation tells us more, but also reveals new uncertainties. The more we watch R2 SWAN, the more we realize how little we truly understand about what it's going to do next. In the next part, we'll widen the lens. Other space rocks have surprised us. The story of tiny asteroids that we only caught after they zoomed past. Because if you think R2 SWAN is an isolated case, you haven't been paying attention. Part 4. The two asteroids that woke us up. If space rocks of a few meters can slip past us and surprise us, Imagine what a comet with fragmentation could do. On October 1st, 2025, an asteroid designated 2025 TF screamed past Earth at an altitude of 428 kilometers. That's about 266 miles. To give you a sense of scale, the International Space Station orbits at roughly 400 kilometers. The Hubble Space Telescope sits at about 535 kilometers. 2025 TF passed through the space where our satellites live. The asteroid was somewhere between 1 and 3 meters across, roughly 3 to 9 feet. Not big enough to survive atmospheric entry intact. If it had hit Earth instead of missing, it would have exploded in an airburst, probably doing little more than creating a spectacular fireball and maybe rattling some windows. Tunguska this was not. But here's the part that should make you sit up straight. We didn't detect it until after it had already flown by. The Catalina Sky Survey picked it up hours after closest approach. Hours! By the time we knew it existed, it was already receding into the distance. If its trajectory had been slightly different, if it had been aimed at Earth's atmosphere instead of skating just above it, the first sign of its existence would have been a bright flash over some unsuspecting city, and a confused population wondering what just exploded overhead. 2025 TF came at us from Antarctica's direction, from the south. It approached during daylight hours for most observation sites. It was small, dark, and fast. Every factor worked against detection, and this wasn't some freak occurrence, someone in a billion cosmic coincidence. This was a gap in our coverage, laid bare. Less than a week earlier, another asteroid, 2025 TQ2, had done something similar. It passed about 3,014 miles, roughly 4,851 kilometers, over Canada. Larger distance than TF, but still uncomfortably close by astronomical standards. And again, we detected it mere hours before or around the time of closest approach. Not days, not weeks, hours. Think about what this means. These were small objects, true. Probably not civilization enders even in a direct impact scenario, but the detection problem scales. If we're missing rocks the size of cars until they're already on top of us, what else are we missing? What about the 10-meter objects, the ones that could take out a city? What about the 50-meter objects, regional devastators? What about something bigger or worse, something that breaks apart on approach and spreads its destruction across multiple impact sites? The Catalina Sky Survey, by the way, is one of the premier near-Earth object detection programs. They're good at what they do. They found thousands of asteroids. The fact that they missed these two until the last moment isn't a failure of the survey. It's a failure of coverage. There are only so many telescopes, scanning only so much sky, only so often. Gaps are inevitable. And here's where the geography matters. Most major surveys are concentrated in the northern hemisphere. The southern sky is underobserved. An object approaching from the south, especially one on a trajectory that keeps it in daylight sky for northern observers, has a much better chance of slipping through unnoticed. Add in the fact that small objects reflect very little light, making them faint and hard to spot even when they're close, and you've got a recipe for surprises. The space agencies responded to 2025 TF's flyby with the expected statements. Yes, we're aware. No, there was no danger. The object was too small to pose a significant threat. We're working on improving detection capabilities. All true statements, all inadequate responses. Because the problem isn't that we got lucky this time. The problem is that we need to get lucky every time. One miss, one object we don't catch, and people die. Maybe not from these particular asteroids, but from the larger cousin we miss next year, or the year after. Now, extrapolate this to comets. An asteroid is a relatively simple threat. It's a solid object, more or less, following a predictable path governed by gravity. You calculate its orbit, you figure out if it's going to hit, and you either sound the alarm or you don't. Comets are nightmares by comparison. They outgaze, they fragment, they shed debris. A comet's nucleus might be 10 kilometers across, but its coma could span 100,000 kilometers. Its dust tail could stretch millions of kilometers. Its debris trail could extend along its entire orbit. If a comet were to disintegrate near Earth, we wouldn't be tracking one object. We'd be tracking a swarm. Some pieces would be large enough to track individually. Others would be too small to see until they hit the atmosphere. The debris would spread out over time, creating a hazard zone that Earth might pass through over hours or days. You can't evacuate a planet. You can't shield an entire hemisphere, your options become extremely limited, extremely fast, and the detection problem is even worse with comets than with asteroids. Asteroids are predictable. Once you've tracked one for long enough to nail down its orbit, you can project its path decades into the future with high confidence. Comets, with their non-gravitational forces and fragmentation risks, remain uncertain even after months of observation. You never quite know what they're going to do until they do it. R2. SWAN is, in many ways, a more complex version of the 2025 TF problem. Both were detected late. Both approached from difficult angles. Both revealed gaps in our surveillance network. The difference is that R2 SWAN is larger, more active, and potentially more dangerous if things go wrong. It's a wake-up call written in hydrogen emissions and green comas, a preview of what a real comet threat might look like if we're not prepared. The lesson from 2025 TF and TQ2 isn't that small asteroids are terrifying. It's that our detection system has blind spots, and those blind spots are big enough to hide genuine threats. Comets, with their unpredictable behaviour and debris fields, exploit those blind spots even more effectively than asteroids do. If we can't catch a 3-metre rock until it's already passing satellite altitude, how confident should we be in our ability to catch a fragmenting comet with a debris field the size of Earth's orbit? So is R2 SWAN dangerous? In this next part, we'll step back and assess whether it's a threat, and if not, why this kind of object is nonetheless a red flag. Because the danger isn't always in the thing itself, sometimes it's in what the thing reveals about everything else we're not seeing. Part 5. Synthesis. R2. SWAN as a warning flag, not panic. R2. SWAN isn't a doomsday object as far as we know. But the real danger is in what it reveals about our blind spots. You need to understand something about risk assessment in planetary defense. It's not just about calculating whether a specific object is going to hit Earth. It's about evaluating the entire threat landscape, identifying vulnerabilities, and building systems that reduce the chance of being surprised. R2. SWAN, by itself, is probably not going to kill anyone. Its current trajectory puts it at a safe distance. Its nucleus is likely small enough that even a worst-case fragmentation scenario wouldn't produce impacts capable of global devastation. But that's not the point. The point is that we didn't see it coming until it was already past perihelion. The point is that its discovery depended on a single instrument that wasn't designed for planetary defense. The point is that its orbit is still uncertain because of outgassing forces we can't precisely model. The point is that if this comet were slightly larger, slightly more active, or on a slightly different trajectory, we could be having a very different conversation right now. Let's walk through what went wrong and what went right. The geometry was against us from the start. R2 SWAN approached from the direction of the Sun, staying hidden in solar glare during its inbound leg. Our ground-based telescopes, which form the backbone of near-Earth object surveys, couldn't see it. Our space-based assets, most of which look outward from Earth's orbit, couldn't see it. The only reason we found it at all was because SWAN happened to be looking at the Sun from a different angle, detecting hydrogen emissions that betrayed the comet's presence. That's a success, technically. We did detect it. But it's a success built on luck, not on robust system design. If SWAN hadn't been operational, if its detectors had been in a maintenance cycle, if Bezoogly hadn't been reviewing the data that week, R2 SWAN might have passed through the inner solar system completely unnoticed. We would have remained blissfully ignorant of a comet making a close approach to Earth, and we'd only learn about it years later when orbital back calculations revealed what we'd missed. The instrument gap is glaring. We need dedicated sensors positioned to monitor the near-Sun region continuously. We need ultraviolet and hydrogen detectors optimized for comet detection, not just solar wind studies. We need infrared surveys with better cadence and coverage. We need southern hemisphere telescopes to fill the geographic gaps. And critically, we need all of these systems integrated into a single alert network, sharing data in real time, cross-checking detections, and providing rapid follow-up observations to nail down orbits. The comet's small nucleus and low activity level made it harder to detect early. If it had been more reflective, or if it had started out gassing earlier in its approach, we might have caught it sooner. But we can't rely on comets being conveniently bright and active. We need to be able to detect faint, inactive objects too. That means more sensitive instruments, more sky coverage, and better algorithms for picking out moving objects against the stellar background. Non-gravitational drift uncertainties remain a problem. Even with weeks of observations, R2, SWAN's exact trajectory at closest approach still carries error bars. Those errors propagate from our incomplete understanding of how much gas and dust the comet is shedding, and how that material is distributed around the nucleus. We need better physical models of cometary activity, informed by close-up observations from spacecraft missions. We need faster orbital calculations that incorporate real-time activity measurements, and we need contingency plans for rapid trajectory changes if a comet suddenly fragments or outbursts. So what should we do? The priority pivots are clear. First, increase funding for missions and instruments dedicated to near-Sun and solar hemisphere monitoring. A constellation of small satellites equipped with ultraviolet and hydrogen detectors could provide continuous coverage of the region where ground telescopes can't look. Second, better integration between the solar physics and planetary defense communities. These groups operate in separate silos right now, using different data formats and communication channels. A comet detected by a solar instrument should automatically trigger alerts to planetary defense networks. Third, use artificial intelligence and machine learning to mine archival data for early faint signals. SWAN has been operating for decades. Its archives probably contain evidence of other comets that were too faint or too brief to notice at the time, but could be retroactively identified with modern algorithms. Fourth, establish rapid coordination protocols for real-time orbit updates during active phases. When a comet is outgassing heavily and its trajectory is uncertain, we need daily, maybe even hourly updates based on fresh observations. Observers around the world need to be mobilized, sharing data through standardized systems. And fifth, public communication. The more eyes on the sky, the better. Amateur astronomers have made critical discoveries in the past. Engaging citizen scientists, providing them with tools and training, and integrating their observations into professional networks could multiply our effective detection capacity. R2. SWAN is a warning flag. It's a reminder that the solar system is not a tame place, and our surveillance of it is far from complete. We've gotten lucky so far. We've caught most of the big asteroids, the ones that could end civilization. We've dodged the bullets we didn't see coming, but luck runs out. Eventually something will slip through the cracks, and by the time we notice, it'll be too late to do anything but watch. The goal of planetary defense isn't to stop every possible impact. That's not realistic. The goal is to maximize our warning time so that if something dangerous is coming, we have options. Right now, for certain classes of objects, particularly comets, approaching from the solar direction, our warning time is effectively 0. That needs to change. In Act 2, we'll begin to pry open the most intriguing mysteries. Where did this comet really come from? Could it fragment? Are there hidden angles the institutions don't want you to see? Because the story of R2 SWAN isn't just about detection failures. It's about what this object is, where it's been, and what it might still do. And that story gets strange. Part 6. Orbital Forensics and Origins. Oort cloud or something else. R2. SWAN might not be just another Oort cloud visitor. The data is ambiguous, and that ambiguity is provocative. Comets have origins. They're not just random balls of ice that appear out of nowhere. They come from specific regions of the solar system, reservoirs of primordial material left over from the formation of planets 4.6 billion years ago. Most comets we see fall into two broad categories: short-period comets, which orbit the Sun in less than 200 years and originate from the Kuiper Belt, that donut-shaped region beyond Neptune filled with icy bodies, and long-period comets, which take centuries or millennia to complete one orbit and originate from the Oort cloud, a vast spherical shell of comets surrounding the solar system at distances up to 100,000 astronomical units. R2, SWAN's orbital elements suggest it's a long-period comet, probably from the Oort cloud. Its eccentricity, a measure of how elongated its orbit is, sits at 0.9993699. That's extremely close to 1, which would be a parabolic orbit, the boundary between bound and unbound trajectories. Anything above 1, and the object is on a hyperbolic escape trajectory, never to return. Anything below 1, and it's gravitationally bound to the Sun, even if it takes millions of years to come back. R2, SWAN's inclination, the tilt of its orbit relative to Earth's orbital plane, is 4.47 degrees. That's relatively low for an Oort cloud comet, which can come at us from any angle. But it's not unprecedented. The perihelion distance, its closest approach to the Sun, was 0.503 astronomical units, just inside Mercury's orbit. The aphelion, its farthest point from the Sun, is calculated at roughly 1,596 astronomical units. That puts the far end of its orbit well beyond the Kuiper belt, out in the inner Oort cloud or scattered disk region. But here's where things get murky. Those orbital elements are based on a short observational arc, just a few weeks of tracking. And they're sensitive to non-gravitational forces, which we know are active because the comet is outgassing. Small errors in modelling those forces can produce significant errors in the calculated orbit. The aphelion distance, in particular, is highly uncertain. It could be longer or shorter by hundreds of astronomical units. That uncertainty matters because it affects our understanding of where the comet came from and whether it's been here before. Long-period comets from the Oort cloud are thought to be pristine, barely altered since the solar system's formation. They spend most of their existence in the deep freeze of interstellar space, only warming up when gravitational perturbations from passing stars or galactic tides nudge them into the inner solar system. If R2 SWAN is a true Oort cloud comet on its first passage through the inner solar system, it's a time capsule, carrying information about the primordial solar nebula. But there's another possibility. Some comets have histories. They've passed through the inner solar system before, maybe many times, and each passage alters their orbits slightly. Gravitational interactions with planets, especially Jupiter, can deflect comets, changing their perihelion distances, inclinations, and orbital periods. Over time, a long-period comet can be captured into a short-period orbit or ejected from the solar system entirely. R2. SWAN's relatively low inclination hints that it might have experienced such interactions in the past. There's also the question of direction. Some researchers, notably Avi Loeb, have noted that R2 SWAN's trajectory doesn't align with that of 3I Atlas, ruling out any connection between the two objects. That's actually reassuring, because it means we're not dealing with some coordinated arrival of multiple objects. But it also raises questions about the statistical distribution of comet orbits. Are we seeing more comets than expected from certain directions? Is there structure in the Oort cloud that we don't fully understand? Exotic origin speculations, and I want to be very clear that these are speculative, include the possibility that R2 SWAN is a dynamically evolved object from the inner Oort cloud, or the scattered disk, regions that are closer to the planets and more influenced by their gravity. Objects from these regions might have been scattered outward by Neptune billions of years ago, spending eons in distant orbits before being perturbed back inward. If true, R2 SWAN could tell us about the solar system's early dynamical history, the era when planets were migrating and flinging debris in all directions. There's also the remote possibility, purely theoretical and unsupported by current data, that R2 SWAN could be weakly bound to the solar system, orbiting in the outer reaches, but not quite escaping. Such objects would be difficult to distinguish from true Oort cloud comets without very precise orbital measurements. The distinction matters for understanding the population and origin of long-period comets. To resolve these questions, we need more data. A longer observational arc would tighten the orbital uncertainties. Spectroscopic observations could reveal the comet's composition, the ratios of different ices and volatiles, which in turn could tell us about the temperature and conditions where it formed. If R2 SWAN's ice chemistry matches that of other Oort cloud comets, we can be more confident in its origin. If it shows anomalies, unusual ratios of deuterium to hydrogen, or unexpected abundances of carbon monoxide or methane, that might suggest a different formation history. Activity profiles matter too. How a comet behaves as it approaches and recedes from the Sun depends on what it's made of and how pristine it is. First-time visitors from the Oort cloud often show distinctive patterns, asymmetric brightness curves, sudden outbursts as fresh ice becomes exposed. If R2 SWAN's activity matches these patterns, it supports the Oort cloud hypothesis. If it behaves more like a short-period comet, with steady, predictable outgassing, that might indicate it's been through the inner solar system before. The isotope ratios are particularly telling. Deuterium, heavy hydrogen, is more common in water ice formed in the cold outer regions of the solar system. By measuring the deuterium to hydrogen ratio in R2 SWAN's coma, scientists could estimate the temperature of the environment where its ice originally condensed. If that temperature is consistent with the Oort cloud's formation region, probably somewhere between the orbits of Uranus and Neptune before being scattered outward, we've got a match. If it's different, we've got a puzzle. Unfortunately, getting detailed spectroscopy of a comet requires large telescopes and favourable observing conditions. R2. SWAN is currently approaching Earth, which will make it brighter and easier to study over the coming weeks, but it's also moving fast, and its activity level is changing. By the time it reaches closest approach on October 20th, it might be too close to the Sun again for some observations. After that, it'll recede, growing fainter, and the window for detailed study will close. The origin question isn't just academic. It shapes our expectations about what R2 SWAN might do next. Oort cloud comets, if they're truly pristine, can be more volatile and unpredictable. They haven't been weathered by multiple passes near the Sun. Their surface layers are fresh, and when sunlight starts vaporizing ice, the release can be explosive. Fragmentation is more common among long-period comets for this reason. The nucleus hasn't been baked and stabilized by repeated thermal cycles. If R2 SWAN is a returning visitor, one that's been through the inner solar system before, it might be more stable. Its most volatile ices would have been stripped away on previous passes. Its nucleus might have developed a dust mantle, a crust of non-volatile material that insulates the remaining ice and moderates outgassing. Such comets are less likely to fragment catastrophically, though they're not immune to it. The ambiguity in R2 SWAN's origin feeds into the uncertainty about its behaviour and its risk profile. We're not just tracking a dot moving across the sky. We're trying to understand a complex evolving object with a history we can only infer from incomplete data. Every observation helps, but the full picture remains frustratingly out of reach. And here's the uncomfortable part. Even if we perfectly understood R2 SWAN's origin, even if we had spectroscopy and isotope ratios and a decade of orbital tracking, we still couldn't predict with absolute certainty what it's going to do. Because comets are chaotic systems. They're governed by physics, yes, but also by contingency. A single pocket of volatile ice exposed at the wrong moment can change everything. A structural weakness in the nucleus, inherited from its formation billions of years ago, can lead to sudden disintegration. The universe is deterministic in principle, but in practice, when you're dealing with objects this complex, prediction becomes probabilistic at best. Next, we'll talk about comet physics that scare engineers, fragmentation, debris trails, and microhazards. Because the threat from a comet isn't just the nucleus, it's everything the nucleus leaves behind. Part 7. Comet physics that scare engineers, fragmentation, debris trails, and microhazards. When a comet breaks, you don't get one danger. You get a whole cloud of them. Engineers who design spacecraft and satellites have nightmares about comets. Not the big, obvious impact scenarios that make Hollywood films. The subtle stuff. The debris, the dust, the tiny particles moving at tens of kilometers per second that can punch through metal like it's tissue paper. When you're trying to keep a billion-dollar satellite operational or protect astronauts on the International Space Station, comets represent a threat that's difficult to quantify and almost impossible to shield against completely. Let's talk about fragmentation. Comets break apart. It's what they do. The historical record is full of examples. In 1994, comet Shoemaker-Levy 9 approached Jupiter and tidal forces ripped it into more than 20 distinct fragments, each one subsequently slamming into the planet in a spectacular week-long bombardment visible from Earth. The impacts released energy equivalent to millions of nuclear weapons, leaving dark scars in Jupiter's atmosphere that persisted for months. Comet 73P Schwassmann-Wachmann 3 has fragmented multiple times. In 1995, observers noticed it had split into multiple pieces. By 2006, it had broken into over 60 distinct fragments, each following a slightly different orbit. The fragments ranged in size from tens of meters to a few hundred meters, and they continued to break apart further as they orbited the Sun. The comet essentially dissolved, transforming from a single nucleus into a stream of debris spread along its orbital path. Fragmentation happens for several reasons. Thermal stress is a big one. As a comet approaches the Sun, the side facing the sunlight heats up dramatically, while the shadowed side remains frozen. This temperature gradient creates mechanical stress, expanding some regions while others stay rigid. If the nucleus has pre-existing cracks or weak points, Thermal stress can propagate fractures until pieces break off. Rotational forces matter too. Comets spin, and as they outgaze, the jets of material escaping from the surface can act like tiny rocket engines, changing the rotation rate. If a comet starts spinning too fast, centrifugal force can overcome the weak gravity and internal cohesion holding it together. The nucleus literally flies apart, shedding chunks that become independent objects. Volatile pockets are another fragmentation mechanism. If a comet has regions rich in highly volatile ices, carbon monoxide, or carbon dioxide, or even methane, and those regions become suddenly exposed to sunlight, the ice can vaporize explosively. The pressure release can blow material off the nucleus, creating an outburst and potentially fragmenting the entire structure if the explosion is violent enough. Now, imagine R2 SWAN fragmenting near Earth. Let's model a hypothetical scenario, strictly for illustration. Suppose the nucleus, maybe 3 to 5 kilometers across, splits into 10 major fragments, ranging from a few hundred meters to a kilometer in size, plus hundreds of smaller pieces from 1 meter up to 10 meters, plus countless grains of dust and ice down to microscopic scales. Each fragment inherits slightly different velocity from the breakup event. Some are thrown forward along the orbit, some are ejected backward, some are pushed sideways. Over time, these velocity differences cause the fragments to spread out, forming a debris cloud that elongates along the comet's trajectory. After a few weeks, the cloud might span millions of kilometers. If Earth's orbit intersects this debris cloud, we're in for trouble. The larger fragments, assuming they're tracked, could be assessed individually for collision risk. But the smaller pieces, the 1 to 10 meter rocks, are much harder to detect and track. They're too small to see from a distance, but large enough to cause serious damage if they hit. And there would be hundreds of them, each on a slightly different path, making individual tracking and prediction nearly impossible. Then there's the dust. Cometary dust particles range from microns to millimeters in size. They're too small to survive atmospheric entry. They'd burn up as meteors, but in space, they're dangerous. A particle a few millimeters across, traveling at 30 kilometers per second relative to a satellite, carries enormous kinetic energy. It can penetrate solar panels, puncture fuel tanks, damage sensors, or create cascading debris from the impact. The International Space Station has shielding designed to handle small particle impacts, layers of material spaced apart so that an incoming particle vaporizes on the outer layer and the resulting plasma disperses before reaching the inner hull. But the shielding has limits. It's designed for typical micrometeoroid flux, the background rain of tiny particles that constantly pelts everything in orbit. A comet debris field passing through Earth's vicinity could increase that flux by orders of magnitude, overwhelming the shielding and causing multiple failures across different spacecraft. Debris trails extend along the comet's entire orbit. Even after the nucleus passes by, even after the major fragments are gone, the dust and small particles remain, forming a meteoroid stream. If Earth passes through this stream, we see a meteor shower, bright streaks in the sky as particles burn up in the atmosphere. Most are harmless, spectacular but non-threatening. But occasionally, larger particles survive long, enough to reach the ground, becoming meteorites. And if the flux is high enough, if the stream is particularly dense, the cumulative atmospheric heating from thousands of meteors entering simultaneously could have localized effects on atmospheric chemistry and temperature. Are cometary debris hazards tracked routinely? The answer is, not as well as they should be. Agencies like NASA and ESA maintain models of known meteoroid streams, predicting when Earth will pass through them and what the expected flux will be. But these models are based on historical observations of meteor showers and back calculations of parent comet orbits. For a newly discovered comet like R2 SWAN, there's no historical data. Any debris field it creates would be a surprise, detectable only when Earth actually passes through it, or when satellites start reporting anomalous impacts. Modelling dust fields in real time is difficult. You need to know the comet's activity level, how much dust it's producing, the size distribution of particles, their ejection velocities, and how they spread out over time. All of these parameters are uncertain, especially for a comet we've only been watching for a few weeks. Dust particles are also affected by solar radiation pressure, the force of sunlight pushing on them, which causes smaller particles to drift away from the comet's orbit faster than larger ones. This creates a complex, time-evolving structure that's challenging to predict. The risk isn't binary. It's not impact versus safe. There's a whole spectrum of hazards. Direct nucleus impact catastrophic for Earth. Large fragment impact regionally devastating. Small fragment impact city-scale damage. Debris field intersection, satellite damage and potential Kessler syndrome, cascading collisions creating more debris. Dust field intersection, increased meteor flux and potential atmospheric effects. Each of these scenarios requires different detection thresholds, different warning times, and different response strategies. And here's the thing that keeps engineers awake at night. You can armor a spacecraft against expected micrometeoroid flux. You can design redundancy into critical systems. You can plan evasive maneuvers if you know a debris cloud is coming. But you can't do any of that if you don't know the debris exists until it's already hitting you. Detection and early warning are everything. Without them, you're flying blind, hoping that luck holds, hoping that the debris misses, hoping that the comet stays intact. R2 SWAN hasn't fragmented yet. It's showing activity, jets, and outbursts, but the nucleus appears to be holding together. That could change. Every day it spends near the sun is another day of thermal stress, another cycle of heating and cooling, another opportunity for a weak point to fail. If it makes it through perihelion intact and continues outbound without breaking apart, we'll probably be fine. If it doesn't, we'll find out very quickly whether our tracking and prediction systems are up to the challenge. In the next part, we'll shift focus from the physics to the systems, the institutional blind spots. Why we're always surprised? Because the technology exists to detect these threats. The science is understood. So why do we keep getting caught off guard? The answer lies in budgets, bureaucracy, and the frustrating gap between what we could do and what we actually do. Part 8. The institutional blind spots. Why we're always surprised. We didn't fail because we lacked tools. We failed because we don't coordinate tools. There's a saying in planetary defense circles, the asteroid that kills us will be the one we didn't see coming. It's meant to be motivational, a call to increase funding and improve detection. But it's also a diagnosis of a systemic problem. We have the technology to find dangerous objects. We have telescopes, sensors, computers, and skilled people. What we don't have is a coherent integrated system that uses all of those assets effectively. Consider the detection of R2 SWAN. It was found by SWAN, an instrument aboard SOHO, a solar physics mission launched in 1995. SWAN wasn't built to find comets. It was built to study the solar wind, the stream of charged particles flowing from the sun that shapes space weather around Earth. The fact that it detects comets at all is a side effect of its design. It sees hydrogen, Lyman alpha emissions, and comets happen to produce those emissions when they outgas near the sun. The solar physics community and the planetary defense community operate in different worlds. They attend different conferences, they publish in different journals, they report to different funding agencies. A solar physicist looking at SWAN data is thinking about coronal mass ejections and solar wind velocity. They're not necessarily thinking about Earth impact hazards. It takes someone like Vladimir Bezugli, someone with a foot in both worlds, to recognize that a hydrogen emission source in SWAN imagery might be a comet that planetary defense people need to know about. This is not a criticism of individuals. Bezugli did exactly what he should have done. He recognized the comet, reported it immediately, and triggered the follow-up observations that refined its orbit. But the system shouldn't depend on one person happening to notice something. It should be automated, robust, redundant. SWAN data should be routinely scanned by algorithms designed to detect comets. Positive detections should automatically trigger alerts to planetary defense networks. Follow-up observations should be coordinated in real time, with telescopes around the world sharing data through standardized systems. We don't have that. What we have is a patchwork of surveys, each operating independently, each with its own cadence and coverage pattern, each reporting detections through different channels. The Catalina Sky Survey, Pan-STARRS, Atlas, TF, and others do heroic work finding asteroids and comets, but they're focused on visible light observations, and they're limited by geography, weather, and the need to avoid pointing near the sun. There are coverage gaps you could fly a comet through, literally. The southern hemisphere is underobserved because most major telescopes are in the north. Regions near the sun, within about 20 degrees elongation, are avoided by most surveys because the sky is too bright, and pointing close to the sun risks damaging sensors. The result is a blind spot, a cone of sky centered on the sun, where objects can hide until they're already close. SOHO and SWAN help fill part of that gap, but they're not optimized for planetary defense. Stereo, another solar mission with 2 spacecraft positioned ahead of and behind Earth in its orbit, can also detect comets from unique vantage points. PUNCH, the polarimeter to unify the corona and heliosphere mission, recently launched, will provide more solar corona observations. But again, these are solar physics missions. The data they produce is valuable for planetary defense, but accessing and processing that data in real time requires coordination that doesn't always happen. The institutional silos are real. Solar physics teams focus inward toward the sun. Planetary defense teams focus outward toward asteroids and comets in Earth-crossing orbits. Rarely do they share data pipelines or alert protocols. Funding flows along disciplinary lines. A proposal to build a new visible light survey telescope, like the Vera C. Rubin Observatory, formerly known as LSST, gets enthusiastic support because it serves multiple science goals: finding transients, mapping the galaxy, studying dark energy. A proposal to build a dedicated near-Sun ultraviolet telescope for planetary defense has a harder time competing for funds because it serves one narrow purpose. Prestige and career incentives play a role too. Publishing a paper about a new asteroid discovery is routine. Publishing about a new detection method or a systemic improvement to alert networks is less glamorous, but potentially more important. Scientists respond to incentives. If the incentive structure rewards individual discoveries over systemic improvements, that's what you'll get. Archival data mining is another missed opportunity. SOHO has been operating since 1995. That's 3 decades of continuous solar observations, including SWAN hydrogen imagery. How many faint comets passed through SWAN's field of view over those decades? Too faint to notice in real time, but detectable with modern image processing and machine learning. Probably dozens, maybe hundreds. Going back and reprocessing those archives could reveal early appearances of known comets, refining their orbits, or even discovering previously unknown objects that could be linked to current threats. But archival mining is slow, labour-intensive and unglamorous. It doesn't produce splashy headlines. It requires computational resources, storage and expertise, and critically it requires someone to fund it. Grants agencies prefer projects with clear, immediate deliverables. Archival mining is speculative. You might find something useful, or you might not. That uncertainty makes it a hard sell. The concrete fixes are straightforward in principle. Establish cross-agency protocols for sharing solar physics data with planetary defense networks. Create standardized alert formats that work across different detection systems. Deploy artificial intelligence tools to scan solar instrument data in real time, flagging potential comets automatically. Fund dedicated near-Sun telescopes, where the ground-based systems using specialized techniques to observe close to the Sun, or space-based sensors positioned at different points in Earth's orbit, or even at the Sun-Earth Lagrange points. Build redundancy into the system. Don't rely on a single instrument or a single observer. Have multiple sensors looking at the same region of sky from different angles, using different wavelengths, so that if one misses something, another catches it. Coordinate follow-up observations automatically, so that when a new object is detected, telescopes around the world immediately start tracking it to nail down its orbit, and fund it properly. Planetary defense is chronically underfunded relative to its importance. The annual budget for NASA's Planetary Defense Coordination Office is measured in tens of millions of dollars. That's a rounding error in the federal budget. For the cost of a single fighter jet, you could build and operate a network of small telescopes that would dramatically improve our detection capabilities. The return on investment, preventing even a single city-scale impact, would be enormous. But funding requires political will, and political will requires public awareness. Most people don't think about asteroid or comet impacts because they're rare on human timescales. We haven't had a major impact event in living memory, unless you count the Chelyabinsk meteor in 2013, which injured over 1,000 people but didn't kill anyone. The threat feels abstract, distant, like worrying about being struck by lightning. Except, lightning strikes millions of times per year. Major impacts are rarer, but their consequences are far worse. The system redesign has to happen at multiple levels: technical, better sensors and algorithms; organizational, breaking down silos and improving coordination; financial, increasing funding and making it sustainable; and cultural, shifting the incentive structure so that systemic improvements are valued as much as individual discoveries. R2 SWAN is a case study in what happens when those elements aren't in place. We got lucky. Bazoogley was paying attention, SWAN was working, the comet was active enough to detect. The follow-up observations came together, the orbit was calculated, everything worked barely at the last possible moment. Next time, we might not be so lucky, and that's not a gamble we should be taking. Next, we'll enter different territory: conspiracies, misinformation vectors, and wild claims. Because wherever there's mystery and incomplete information, speculation rushes in to fill the void. Some of it is harmless fun, some of it is dangerous nonsense, and some of it, the most interesting part, sits in that uncomfortable space between plausible and absurd, where you can't quite dismiss it but can't quite accept it either. Part 9. Conspiracies, misinfo vectors and wild claims. Where there's mystery, conspiracies rise. But let's separate what is implied from what's real. The internet loves a good conspiracy theory. It's human nature. When confronted with uncertainty, ambiguity, or events that feel significant but aren't fully explained, our brains fill in the gaps. We see patterns where none exist. We connect dots that shouldn't be connected. We elevate coincidences into evidence and speculation into certainty. Space, with its vastness and mystery, is particularly fertile ground for this kind of thinking. R2, SWAN, discovered late, approaching Earth, exhibiting unusual activity, is exactly the kind of object that attracts conspiracy theories. So let's address them, not to mock or dismiss, but to think critically about what's plausible and what isn't. Because the line between healthy skepticism and unfounded paranoia is important, and it's worth knowing where that line sits. Common themes in space conspiracies revolve around hidden agendas. Governments know more than they're telling us. Space agencies are covering up evidence of alien artifacts or incoming threats. Objects like R2 SWAN aren't natural, they're engineered, sent by an extraterrestrial intelligence for purposes we can only guess at. These claims tap into a deeper anxiety about control and knowledge. If the authorities are lying to us about what's in space, what else are they lying about? Let's start with the claim that R2 SWAN might be artificial. An alien probe, perhaps, designed to look like a comet but actually performing reconnaissance or seeding our planet with something. Biological agents, nanotechnology, who knows? It's a thrilling idea, the kind of premise that drives science fiction novels. But what does the evidence actually say? Everything we've observed about R2 SWAN is consistent with a natural comet. It has a coma, glowing green from diatomic carbon and cyanogen, exactly what you'd expect from sublimating ice rich in organic compounds. It has a tail shaped by solar wind and radiation pressure, following the physics that govern all cometary tails. It exhibits outbursts, sudden brightenings caused by volatile pockets vaporizing, a behavior seen in dozens of natural comets. Its orbit fits the profile of a long-period comet from the Oort cloud, with an eccentricity and trajectory consistent with gravitational perturbations nudging it inward from the outer solar system. There's no anomaly here, no deviation from expected behavior, no signal hidden in the spectral data suggesting artificial materials or propulsion. If R2 SWAN were a probe, it would be the most elaborate deception imaginable, perfectly mimicking every chemical, thermal and dynamical characteristic of a natural object. Possible? In the abstract sense that we can't prove a negative? Yes. Plausible? No. The simplest explanation, the one that requires no additional assumptions, is that it's exactly what it appears to be, a comet. But conspiracy theories don't die from lack of evidence. They thrive on it. The absence of proof becomes proof of cover-up. If scientists haven't found evidence of artificiality, maybe they're not looking hard enough, or maybe they found it and aren't telling us. This is the unfalsifiable core of conspiracy thinking. Any data that contradicts the theory is dismissed as fabricated or incomplete. Any lack of data is interpreted as suspicious. Compare this to the treatment of 3i Atlas, which has generated its own share of sensational claims. Is it interstellar? Maybe, though the jury is still out. Is it artificial? Almost certainly not, but that hasn't stopped speculation. The difference is that 3i Atlas has been studied extensively. Multiple telescopes have observed it. Its trajectory has been calculated with high precision. Its spectrum has been analysed. The weight of evidence points toward a natural object, either a comet or possibly a transition object between comet and asteroid. following a path that could be interstellar but might also be a highly eccentric solar system orbit. The lesson here is that rigorous investigation collapses most sensational claims. Not all, there are genuine mysteries in astronomy that remain unsolved, but most. When you actually gather data, when you apply the tools of science, spectroscopy, photometry, orbital mechanics, the exotic explanations usually evaporate, leaving mundane but accurate answers. So how do you evaluate a sensational claim about a space object? Here's a decision tree, a critical thinking checklist. First, is the claim making an extraordinary assertion? Extraordinary claims require extraordinary evidence. A claim that R2 SWAN is a natural comet requires only ordinary evidence because natural comets are common. A claim that it's an alien probe requires extraordinary evidence because alien probes are, as far as we know, non-existent. Second, is the evidence presented consistent with the claim, or could it be explained more simply? If someone points to R2 SWAN's green coma as evidence of artificiality, ask whether natural processes could produce the same colour. They can. Diatomic carbon is well understood chemistry. If someone points to its late discovery as suspicious, ask whether detection failures for natural objects are common. They are. We've already discussed the asteroid 2025 TF. Third, are the people making the claim qualified to interpret the data? Not everyone with an opinion about space objects has the expertise to evaluate orbital mechanics or spectroscopy. That doesn't mean non-experts are always wrong, but it does mean you should weight their claims accordingly. A professional astronomer saying this orbit is consistent with a natural long-period comet carries more credibility than a random internet user saying this orbit proves it's an alien probe. Fourth, is the claim falsifiable? Can you imagine evidence that would disprove it? If not, if the claim is structured so that any possible observation can be twisted to support it, that's a red flag. Good scientific hypotheses make specific predictions that can be tested. If R2 SWAN were artificial, what would we expect to see that we don't see in natural comets? Anomalous acceleration not explained by outgassing, spectral lines from manufactured materials, radio signals. If none of those are present, the artificial hypothesis loses support. Fifth, what's the alternative explanation, and how does it compare? Occam's razor, the principle that the simplest explanation is usually correct, is a useful guide. It's not a law of nature, but it's a good heuristic. If explaining R2 SWAN requires invoking alien civilizations with technology capable of interstellar travel and elaborate deception, while the natural explanation requires only well-understood physics and chemistry, the natural explanation wins by default unless there's compelling evidence otherwise. Let's look at a few recent examples from forums and social media and deconstruct them. Claim 1, R2 SWAN was discovered right after passing the Sun, which means they're hiding something. Deconstruction, no. It means we have detection blind spots near the Sun, a known problem we've discussed extensively. The late discovery is evidence of surveillance gaps, not cover-ups. Claim 2, the comet's trajectory is too perfect. It's aimed right at Earth. Deconstruction, it's not aimed at Earth. Closest approach is 0.26 astronomical units, over 100 times the Moon's distance. The MOD is larger than the diameter of Earth's orbit. There's no impact trajectory. The feeling that it's aimed at us is a psychological bias. We notice objects that come near us and forget the thousands that don't. Claim 3, the green colour is unnatural. It's a propulsion system leaking fuel. Deconstruction, green coma are extremely common. Comet Lovejoy, Comet Eason, Comet Holmes, dozens of others have shown green coloration from diatomic carbon emissions. It's standard cometary chemistry, not exotic propulsion. Claim 4, why did only one person find it? Why didn't NASA see it first? Deconstruction, NASA doesn't have a monopoly on sky observations. Amateur astronomers and international observers find new objects all the time. Berzugli happened to be looking at SWAN data, which most people don't routinely check. NASA's surveys focus on different regions of sky. This is how distributed observation networks work. The takeaway isn't that all speculation is bad. Curiosity is healthy. Asking questions is how we learn. But there's a difference between asking, could this be artificial, and asserting, this is definitely artificial, and anyone who says otherwise is lying. The first is scientific thinking. The second is conspiracy thinking. Stay curious, not credulous. Engage with the mystery, but demand evidence. Be willing to follow the data wherever it leads, even if it leads to a boring answer. because often, the truth is less exciting than the speculation. R2, SWAN is probably just a comet, a fascinating, scientifically valuable, detection-challenging comet, but a comet nonetheless. And that's okay. The universe doesn't owe us aliens or conspiracies, it just owes us the truth, and finding that truth is hard enough without cluttering it with fantasies. Next, we'll push further into the speculative realm, but staying tethered to logic. Wild cards and fringe speculation. The ideas that sit at the edge of plausibility. Not quite mainstream, but not quite dismissible either. The fun part of science, where you let your imagination run, but keep your skepticism close at hand. Part 10. Wild cards and fringe speculation. Now let's see how far we can push the envelope without quitting science. There's a zone of ideas, a grey area between established fact and obvious nonsense, where things get interesting. These are the hypotheses that don't have enough evidence to be accepted, but aren't absurd enough to be dismissed outright. They're the long shots, the low probability scenarios that nonetheless remain within the realm of physical possibility. In the case of R2 SWAN, several such ideas are worth exploring, not because they're likely, but because considering them sharpens our thinking about what we know and what we don't. Let's start with exotic volatiles. Most comets are primarily water ice mixed with dust and rocky material, but they also contain other ices, carbon dioxide, carbon monoxide, methane, ammonia, various organic compounds. The exact mix depends on where and when the comet formed. Objects that condense farther from the Sun, in colder regions, tend to have higher abundances of highly volatile species like carbon monoxide. If R2 SWAN contains unusually large pockets of such materials, its behaviour could be more erratic than typical comets. Imagine a nucleus with a substantial core of carbon monoxide ice buried beneath a water ice mantle. As the comet approaches the Sun, the outer water ice sublimates first, creating the visible coma and tail. But beneath the surface, the carbon monoxide is warming up, building pressure. Carbon monoxide sublimates at much lower temperatures than water. At some threshold temperature, the pressure becomes too great, the overlying material fractures, and the carbon monoxide explodes, outward in a violent outburst. This could produce the sudden brightenings observed in late September, and it could also impart significant non-gravitational acceleration, altering the comet's trajectory unpredictably. This isn't wild speculation. We know comets contain these materials. Spectroscopy has detected carbon monoxide, carbon dioxide, and other volatiles in cometary comae. The question is one of abundance and distribution. If R2 SWAN has an unusual composition, it could behave in ways that don't fit standard models, making trajectory predictions even more uncertain. Another exotic possibility involves clathrates, ice structures where gas molecules are trapped inside a lattice of water ice. Clathrates can store large amounts of gas in a stable solid form, releasing it suddenly when the structure melts or destabilizes. Methane clathrates, for example, exist on Earth in ocean sediments and permafrost. If cometary ice contains clathrates, they could act as delayed release mechanisms, outgassing long after the comet has moved away from the Sun, or exploding violently if the structure collapses. Cryovolcanism is a more speculative idea. On some icy moons, like Enceladus and Europa, subsurface liquid reservoirs erupt through the surface, creating geysers of water and other materials. Could a comet have similar internal dynamics? It's unlikely. Comets are much smaller and don't have the internal heat sources that drive cryovolcanism on large moons. But if a comet's nucleus were unusually large and had a significant rocky component, radioactive decay or tidal heating during close solar approaches could potentially create localized liquid pockets. Their eruption would look like extreme outgassing, jets of material that don't follow the expected patterns. For each of these ideas, the observational signature would be distinct. Exotic volatiles would show up in spectroscopy as unusual emission lines or abundance ratios. Clathrate destabilization would produce sudden, symmetric outbursts as gas is released uniformly from the interior. Cryovolcanism would create persistent, localized jets that don't correlate with solar heating patterns. If any of these signatures were detected in R2 SWAN, it would be scientifically exciting, a chance to study processes that are rare or theoretical. But so far, nothing definitive has been reported. The comet looks like a comet. Its activity is consistent with standard sublimation physics. The green coma is explained by diatomic carbon. The outbursts are consistent with volatile pockets being exposed. There's no smoking gun pointing to exotic processes, though continued observation might yet reveal something unusual. Now, let's wander into even more speculative territory. What if R2 SWAN's orbit has been perturbed by something we haven't accounted for? Standard orbital calculations include the gravitational influence of the Sun and major planets. For most comets, that's sufficient, but if a comet passes very close to a smaller body, an asteroid, a Kuiper belt object, even a hypothetical undiscovered planet in the outer solar system, that encounter could alter its trajectory. Could R2 SWAN have experienced such an encounter? It's possible, but unlikely. The odds of a close approach to an unknown massive object are extremely low. Space is big, and even the Kuiper belt, crowded by astronomical standards, is mostly empty. Detecting such an encounter would require either catching it in the act, observing the comet's trajectory deviate from predicted values in a way that can't be explained by outgassing, or finding evidence in long-term orbital evolution that something perturbed it. There's also the extremely low probability, almost negligible but not quite zero, idea of artificial acceleration. Suppose, purely for the sake of argument, that R2 SWAN were under some form of directed control, not natural outgassing but deliberate thrust. What would that look like? It would produce acceleration that doesn't correlate with solar distance or orientation. Natural outgassing jets are driven by sunlight, so they're strongest near perihelion and they point away from the sun. Artificial thrust could occur at any time and in any direction. Have we seen such anomalies? No. R2. SWAN's activity fits natural patterns. Its trajectory deviations are consistent with cometary outgassing. There's no evidence of directed acceleration. But, and this is important, our observational coverage is limited. We've been tracking the comet for a few weeks. If artificial acceleration were subtle, producing velocity changes of only a few meters per second over long periods, it might be difficult to distinguish from natural non-gravitational forces given the current data quality and duration. This is where Occam's razor steps in. The natural explanation is vastly simpler and more consistent with observations. Invoking artificial acceleration requires extraordinary evidence, which we don't have. But it's worth noting that the absence of evidence isn't the same as evidence of absence. If we want to rule out exotic explanations definitively, we need better data. More observations, longer tracking arcs, detailed spectroscopy, maybe even a spacecraft mission to get close-up measurements. One last fringe idea, the possibility that archival data hides an earlier detection. SWAN has been operating since 1995. SOHO has other instruments that image the solar corona and could potentially detect bright comets. Stereo, operational since 2006, has captured many sun-grazing comets. What if R2 SWAN appeared faintly in data from months or years ago, too faint to notice in real time, but detectable with modern image processing? This is actually testable. Go back through SWAN and SOHO archives, apply current detection algorithms, and see if anything pops up that matches R2 SWAN's orbital characteristics. If you find early detections, you can extend the observational, arc backward in time, significantly improving orbital accuracy. If you don't find anything, that tells you the comet either wasn't active enough to detect earlier, or it wasn't in SWAN's field of view. Archival mining like this has been successful before. Comets have been discovered in old photographic plates or spacecraft data years after the images were taken. It's tedious work, sifting through terabytes of data, but modern machine learning tools make it more feasible. A trained neural network could scan decades of imagery in days, flagging potential comets for human review. The takeaway from all this speculation is that uncertainty creates opportunity. We don't know everything about R2 SWAN. That's not a failure, it's an invitation. Every unknown is a question waiting to be answered. Some of these questions will have boring answers. The comet is probably just water ice and rock, following a predictable orbit, behaving like thousands of other comets we've observed. But some questions might have interesting answers. Maybe it has unusual composition. Maybe it fragments in an unexpected way. Maybe archival data reveals something surprising. The key is to rank ideas by testability and likelihood. Prioritize hypotheses that make specific predictions and can be confirmed or ruled out with available or near-future observations. Don't waste resources chasing untestable claims or ideas that require violating known physics. But don't be afraid to look at the data sideways, to ask what if, and follow the logic wherever it leads. Science is imagination constrained by evidence. You need both. Imagination without evidence becomes fantasy. Evidence without imagination becomes bookkeeping. The sweet spot is where you let your mind explore possibilities while keeping one hand firmly on the data, ready to abandon ideas that don't work and embrace ones that do, no matter how strange they might seem. Now, in Actor 3, we'll tie this story into the shifting universe of detection technology, artificial intelligence, and the next cosmic surprises we aren't seeing yet. Because R2 SWAN is just one object. There are others out there, undetected, approaching, waiting to test whether we've learned our lessons or whether we'll be caught off guard again. Part 11. News. 1. 2025 as TF's near miss as a reality check. Asteroid 2025 TF passed 428 kilometers above Earth on October 1st, 2025, inside many satellite orbits, and was only detected after the fact. Let's ground ourselves in something concrete, something that actually happened while R2 SWAN was making its approach. On October 1st, in the early hours, an asteroid screamed past Earth at an altitude that should have set off every alarm bell in planetary defense. 428 kilometers. That's lower than many communication satellites. The International Space Station orbits at about 400 kilometers, so 2025 TF passed overhead at roughly the same altitude. The asteroid was small, between 1 and 3 meters across, basically the size of a car. If it had entered Earth's atmosphere instead of skimming past, it would have exploded in an airburst, creating a bright fireball and maybe a sonic boom, but probably not reaching the ground intact. Not a civilization ender, not even a city destroyer, but still, a multi-ton object moving at several kilometers per second, releasing the energy equivalent of several tons of TNT. If that happened over a populated area, it would make headlines. But here's what should scare you. We didn't see it coming. The Catalina Sky Survey detected 2025 TF hours after closest approach. Hours. By the time astronomers knew it existed, it was already past us, receding into space. If its trajectory had been slightly different, if it had been aimed at the atmosphere instead of skating over it, the first warning would have been a flash in the sky and confused reports flooding emergency services. This isn't hypothetical. This actually happened. Not in a simulation. Not in a disaster movie. In real life, on October 1st, 2025, while people were sleeping or going about their daily routines, a space rock passed closer to Earth than most satellites, and we had no idea until after the fact. The timeline is sobering. Closest approach occurred at approximately 0047 UTC over Antarctica. Remote location, sparse population, which is fortunate. Detection came hours later, when Catalina's automated systems flagged a fast-moving object in their images. Orbital calculations were performed. Backtracking revealed that the object had already made its closest approach. Announcements were made to the astronomical community. The general public, for the most part, never heard about it. Why did we miss it? Several reasons, all of which we've discussed in the context of R2 SWAN. 2025 TF approached from the southern sky. Most major surveys are concentrated in the northern hemisphere. It was small, which means it reflected very little sunlight, making it faint and hard to detect. It was fast, moving through the inner solar system quickly, giving surveys limited time to spot it, and it approached during daylight hours for many observatories, further reducing the observation window. These aren't excuses. They're explanations of systemic limitations. Our detection grid has holes. Small, fast objects approaching from certain directions can slip through. 2025 TF did exactly that. It exploited every weakness in our surveillance network and made it all the way to closest approach without being noticed. Now, 2025 TF wasn't dangerous in the catastrophic sense. Its small size meant that even a direct impact would have been localized. But it's a proof of concept. It demonstrates that our early warning system, which works well for large, slow-moving asteroids on predictable orbits, breaks down for small, fast objects on unfavorable trajectories. And here's the connection to R2 SWAN. Comets, especially active ones, are more complex than asteroids. They shed debris, they fragment, they create dust trails. If a comet were to approach from a similar blind spot detected late like 2025 TF, but with the added complications of outgassing and potential fragmentation, we'd be facing a much more difficult situation. Not a single object to track, but potentially dozens or hundreds of fragments, each on a slightly different path, creating a hazard zone that extends across millions of kilometers. The altitude of 2025 TF's pass, 428 kilometers, puts it squarely in low Earth orbit territory. Satellites at that altitude include imaging satellites, weather satellites, communications relays, scientific instruments. If the asteroid had collided with one of them, it would have been catastrophic for that spacecraft. The impact would have created a debris cloud, thousands of fragments spreading out in orbit, each one a potential threat to other satellites. This is the nightmare scenario known as Kessler syndrome, where one collision triggers a cascade of further collisions, progressively filling orbital space with debris until it becomes too hazardous to use. We got lucky with 2025 TF. It missed everything. But luck isn't a strategy. Luck runs out. The question isn't if we'll have another close pass by an undetected object. The question is when, and whether next time we'll be as fortunate. This event should have been a wake-up call. It should have triggered emergency meetings, budget increases, urgent deployments of new detection systems. Did it? Barely. There were a few news articles, some social media discussion among space enthusiasts, a couple of professional publications analysing the detection failure, but no massive policy shift, no sudden influx of funding, no crash program to fill the surveillance gaps. Why? Because 2025 TF didn't hit. It passed by harmlessly, and because nothing bad happened, it's easy to shrug it off. This is the paradox of planetary defense. Successes, preventing impacts, are invisible. You can't prove that your detection system saved lives if the asteroid misses naturally. Failures, missing an object that hits, are catastrophic and obvious, but near misses, objects we didn't see that missed anyway, are ignored. They should be treated as warnings, as evidence that the system isn't working as well as it should. Instead, they're forgotten within days. R2, SWAN and 2025 TF are cut from the same cloth. Both were detected late. Both revealed weaknesses in our surveillance. Both should be driving urgent reform. The difference is that R2 SWAN is larger, more complex, and potentially more dangerous if its behavior changes. But the fundamental lesson is identical. We're not seeing everything we need to see. Objects are approaching Earth without adequate warning, and if we don't fix the system, eventually our luck will run out. Next, we'll look at how artificial intelligence could change this equation. New tools, new methods, new possibilities for catching the threats we're currently missing. Because if human observers and traditional surveys aren't enough, maybe machine intelligence can fill the gap. Maybe. Part 12. News. 2. AI and next-gen agents for transient detection. OpenAI Dev Day announcements. October 2025. GPT-5 Pro, Agent Kit, and the tools that could have caught R2 SWAN earlier. Technology doesn't stand still. While we've been tracking comets and asteroids with telescopes and human analysis, the field of artificial intelligence has been advancing at breakneck speed. In October 2025, OpenAI announced new developments, more capable models, better reasoning, agent frameworks that can perform complex multi-step tasks with minimal human guidance. These aren't just chatbots. They're systems that can process vast amounts of data, recognize patterns, make decisions, and coordinate actions across multiple domains. What does this have to do with comets? Everything. Because the problem with detecting objects like R2 SWAN isn't a lack of data, it's a lack of processing. SOHO's SWAN instrument produces hydrogen imagery continuously. Gigabytes of data flowing down from the spacecraft every day. Most of it is archived, reviewed briefly by solar physicists looking for specific phenomena, and then filed away. A human observer, even a skilled one like Bouzugli, can only look at so much. They have limited time, limited attention, other responsibilities. Things get missed. But an AI agent doesn't sleep. It doesn't get bored. It doesn't have other responsibilities. It can process every single image, every day, looking for anomalies, patterns that might indicate a comet's hydrogen envelope. Movement against the background, brightness changes, anything out of the ordinary, and it can do this in real time, flagging potential detections within minutes or hours of the data arriving, not days or weeks later. Imagine a pipeline built around these new AI tools. SWAN images are ingested continuously from SOHO. A machine learning model, trained on thousands of known comets and their hydrogen signatures, scans each image for potential new objects. When it finds something, it doesn't just log it. It automatically cross-references with ground-based optical surveys. Is there a corresponding visible light detection? If not, it triggers an alert to observers, requesting follow-up imaging. If yes, it initiates automated orbit calculations, combining the hydrogen detection with optical positions to refine the trajectory. This isn't science fiction. The technology exists. Machine learning models for image recognition and anomaly detection are mature. They're used in medical, imaging, satellite analysis, industrial quality control, autonomous vehicles. Applying them to astronomical data is straightforward. The challenge isn't building the algorithms, it's integrating them into existing workflows, getting different observatories and data archives to share information in compatible formats, and convincing institutions to adopt new tools. Few-shot learning, a recent advance in AI, is particularly relevant. Traditional machine learning requires massive training datasets, thousands or millions of examples. Few-shot models can generalize from just a handful of examples. Show the model 10 or 20 known comets in SWAN imagery, and it learns to recognize similar patterns in new images. This dramatically reduces the data requirements and makes it feasible to train specialized models for rare events. The PUNCH mission, which recently launched, will provide new high-resolution imaging of the solar corona and inner heliosphere. Combining PUNCH data with SWAN hydrogen detections and ground optical surveys, all processed by AI models that can recognize cometary signatures across multiple wavelengths, would create a formidable detection network. Objects hiding in solar glare would be caught by PUNCH. Objects producing faint hydrogen emissions would be caught by SWAN. Objects visible in optical light would be caught by ground surveys. And AI agents would tie it all together, coordinating observations and refining orbits in real time. Could this system have caught R2 SWAN earlier? Almost certainly. If an AI had been scanning SWAN data in August and early September, it might have detected faint hydrogen emissions weeks before Bernoulli's manual discovery. That extra time would have allowed for more observations, better orbit determination, earlier assessment of potential hazards. It might have also revealed activity patterns that would help predict the comet's outgassing behavior and trajectory evolution. But there are challenges. False positives are a major concern. AI models, especially those trained on limited data, can mistake noise for signal. They might flag cosmic rays, detector artifacts, or background stars as potential comets. Human review is still necessary to filter out these false alarms. The goal isn't to replace human observers, it's to augment them, to handle the bulk of data processing so that humans can focus on the interesting detections that need expert judgment. Latency is another issue. AI models need computational resources. Processing gigabytes of imagery in real time requires servers, GPUs, bandwidth. For a continuous monitoring system, those costs add up, and there's always a trade-off between speed and accuracy. A fast model that misses half the comets isn't useful. A slow model that catches everything but takes days to process each image isn't much better than manual review. Governance and control are critical questions. Who runs these AI systems? Who decides what gets flagged as a threat? Who has access to the alerts? Planetary defense is an international concern. Detection systems need to be transparent, reliable, and accessible to all nations. An AI controlled by a single country or private entity creates dependencies and potential points of failure. The ideal would be an open, distributed network where multiple independent AI systems scan the data and share findings, with human oversight ensuring quality and preventing abuse. Despite these challenges, the potential is enormous. AI can process more data faster than humans ever could. It doesn't have cognitive biases. It doesn't get tired or distracted. It can monitor multiple data streams simultaneously, looking for correlations that a human might miss. And crucially, it can improve over time. Every new detection refines the model. Every false positive teaches it to discriminate better. The system gets smarter with experience. R2. SWAN's late discovery is a failure of integration, not capability. We had the data. We had instruments sensitive enough to detect it. What we didn't have was a system that automatically scanned that data and connected the dots. AI can be that system. Not a replacement for telescopes or human expertise, but a force multiplier that ensures we actually use the data we're collecting. In the next part, we'll look at a specific application, few-shot AI models spotting cosmic events with minimal training data. Because if we can teach machines to recognize patterns from just a handful of examples, we can deploy detection systems far faster than traditional methods allow. And speed, in planetary defense, is everything. Part 13. News. 3. Few-shot AI models spotting cosmic events. Oxford University, October 2025, demonstrated AI models that detect cosmic transients with minimal labeled data, and what that means for finding the next R2 SWAN. Astronomy generates more data than astronomers can analyze. It's been true for decades, but it's gotten worse as telescopes have improved. Every night, survey telescopes capture millions of images. Each image contains thousands of stars, galaxies, cosmic rays, detector glitches, atmospheric artifacts. Finding the few genuinely interesting objects, the supernova, asteroids, comets, variable stars, among all that noise, is like looking for needles in a haystack the size of a continent. Traditional approaches use carefully designed algorithms, detect objects that move between images, track asteroids, detect objects that brighten suddenly, find supernovae. These algorithms work, but they're rigid. They only find what they're programmed to find. If something unusual happens, something that doesn't fit the expected pattern, it slips through. Machine learning offers an alternative. Instead of explicitly programming rules, you train a model on examples. Show it 1,000 supernovae, and it learns what a supernova looks like. Show it 10,000 asteroids, and it learns to recognize asteroidal motion. The model generalizes, developing an internal representation of the patterns, and can then apply that knowledge to new data. But there's a catch. Training requires labeled data. Someone has to manually identify and categorize thousands of examples. For common events like asteroids or supernovae, we have those datasets. For rare events like unusual comets or exotic transients, we don't. There might only be a dozen examples in the entire historical record. Traditional machine learning struggles with small datasets. It overfits, memorizing the examples instead of learning the underlying pattern. Few-shot learning solves this. Instead of requiring thousands of examples, few-shot models can learn from as few as 5 or 10. They do this by pre-training on massive generic datasets, learning general-purpose pattern recognition, and then fine-tuning on the specific task with minimal examples. It's analogous to how a human learns. You don't need to see 1,000 elephants to recognize an elephant. You see 1 or 2, learn the key features, trunk, big ears, grey skin, and you can identify elephants from then on. Recent work from Oxford, building on advances from multiple research groups, has demonstrated few-shot models applied to astronomical transients. Give the model a handful of known Lyman alpha emissions from comets in SWAN imagery, and it learns to spot similar patterns in new images. Give it a few examples of cometary green comet in optical data, and it can flag potential new comets automatically. The implications for planetary defense are profound. We don't need decades of historical data to build effective detection systems. We can bootstrap from what we have. Take the 50 or 100 best documented comets detected via hydrogen emissions. Train a few-shot model on those examples. Deploy it to scan SWAN archives from the past 3 decades. Any cometary signatures that were too faint or too brief to notice at the time would pop out, retroactively discovered. This archival mining could extend observation arcs for known comets, revealing earlier appearances that refine their orbits. It could also discover entirely new objects, comets that passed through unnoticed but left faint traces in the data, and critically, it would validate the model. If it successfully finds known comets in archival data, we can be confident it will find new ones in real-time data. For R2 SWAN specifically, this approach could answer a key question. Was it visible in SWAN data before September 11th? Berzugli found it on that date, but comets can be active for weeks or months as they approach the Sun. If R2 SWAN started outgassing in late August, producing faint hydrogen emissions, those emissions might be detectable in archived SWAN images with modern processing. Going back and running a few-shot model over August and September, data could reveal the comet's appearance date, extending the observation arc backward and improving orbital accuracy. There are technical hurdles. Archival data isn't always in optimal format. Older images might have lower resolution, higher noise, or incomplete metadata. Pre-processing is required, aligning images, calibrating brightness, filtering out artifacts, and even with few shot learning, some manual validation is necessary. The model will flag candidates, but humans need to confirm which ones are real. But the potential is undeniable. We're sitting on decades of astronomical data that has never been fully analysed. Every major survey, every space mission, has archives that could contain discoveries waiting to be made. Applying modern AI to this legacy data is like getting a second chance, revisiting observations with better tools and finding what we missed the first time around. Beyond archival mining, few-shot models enable rapid deployment of new detection capabilities. If a new class of threat emerges, something we haven't seen before, we don't need years to build a detection system. We need just a few examples to train a model and start scanning for more. This agility is crucial in planetary defense, where the threat landscape can change overnight. Domain shift remains a challenge. A model trained on SWAN hydrogen imagery might not generalize well to stereo or punch data without additional fine-tuning. Different instruments have different characteristics, noise profiles, resolution, wavelength coverage. Few-shot learning helps, but it's not magic. Careful engineering is required to ensure models are robust across different data sources. Collaboration between astronomers and AI researchers is essential. Astronomers understand the physics, the context, what's interesting versus what's noise. AI researchers understand the models, the architectures, the training procedures. Neither group alone can build optimal systems, but together, leveraging domain expertise and technical capability, they can create tools that dramatically improve our detection and characterization of cosmic threats. The lesson from few-shot AI in astronomy is that we don't need perfect data or infinite resources to make progress. We need smart algorithms, targeted datasets, and a willingness to apply new methods to old problems. R2. SWAN's detection might have happened weeks earlier if such tools were operational. The next comet might be caught before it even reaches perihelion, giving us maximum warning time, all because an AI agent flagged a faint signal that a human would have overlooked. Next, we'll draw parallels to another field where fast detection and multi-instrument coordination have become routine. Gravitational wave astronomy and the culture of rapid response that's been built around LIGO and similar observatories. Because planetary defense can learn from that success story, adopting the same protocols and infrastructure that have made multi-messenger astronomy so effective. Part 14, News, 4, LIGO, Gravitational Wave, Alert Networks, and the Culture of Fast Response. The alert came at 3:47 in the morning on August 17, 2017. Most of the world was asleep. But in observatories scattered across 6 continents, astronomers jolted awake to their phones, buzzing with a message that would change everything. LIGO, the Laser Interferometer Gravitational Wave Observatory, had just detected something rippling through the fabric of space-time itself. 2 neutron stars, locked in a death spiral for millions of years, had finally collided. The gravitational waves from that cosmic car crash had just washed over Earth, stretching and squeezing space itself by less than the width of a proton. But here's what made that night different from every other gravitational wave detection before it. Within 11 hours, 70 telescopes around the planet had swiveled to the same patch of sky. Space telescopes, ground telescopes, radio dishes, X-ray detectors, they all saw it. The first kilonova ever witnessed in real time, a fireball forging gold and platinum in quantities that would shame every mine on Earth combined. It was the most coordinated response in the history of astronomy, and it happened because someone built the infrastructure to make fast response not just possible, but automatic. You might be wondering what colliding neutron stars have to do with sun-grazing comets that no one's watching. Everything, actually. Because what LIGO and its partners built over decades of planning isn't just a detector, it's a culture, a philosophy, a worldwide agreement that when the universe does something interesting, you drop everything and look, immediately, with every tool you have. That culture doesn't exist yet for objects threatening Earth from the sun's blind spot, but it should. And the gravitational wave community just handed us the blueprint. LIGO didn't start as a fast response network. When it first came online in 2002, it was essentially screaming into the void, listening for whispers that everyone said were impossible to hear. For years, it heard nothing. The detectors were too crude, the sensitivity too low. Engineers spent a decade upgrading the interferometers, installing mirrors so perfectly smooth that if you scaled them up to the size of Earth, the biggest bump would be 3 meters tall. They stretched laser beams 4 kilometers long and measured changes smaller than 1,000th the diameter of a proton, and still nothing. Then, on September 14, 2015, the upgraded LEGO heard it. 2 black holes, each about 30 times the mass of the Sun, merged 1.3 billion light-years away. The signal lasted 1/5 of a second. It was the first direct detection of gravitational waves in human history, confirmation of a prediction Einstein made a century earlier, but thought we'd never be able to test. But detection was just the beginning. The real challenge was coordination. Gravitational waves don't tell you exactly where they came from. LIGO can narrow it down to a region of sky, sometimes hundreds or thousands of square degrees, depending on how many detectors caught the signal. 1 detector gives you almost nothing. 2 detectors, LIGO's twin facilities in Washington and Louisiana, give you a broad arc across the sky. Add Virgo in Italy, and suddenly you've got triangulation. Add Kagra in Japan, and the uncertainty shrinks even more. But even with 4 detectors, the localization isn't perfect. You need optical telescopes, infrared telescopes, radio telescopes to sweep that region and find the visible counterpart, the actual explosion or merger that caused the ripple. And you need them to move fast because these events fade quickly. So the gravitational wave community built what they call a multi-messenger astronomy network. When LIGO or Virgo detects a candidate event, it doesn't sit on the data for peer review. It doesn't wait for confirmation. It sends an automated alert within minutes to thousands of astronomers worldwide. The alert includes the coordinates, the uncertainty region, the type of event, and an estimate of how confident the detection is. Telescopes with wide fields of view start scanning immediately. Faster instruments take quick looks. Slower, more sensitive telescopes wait for a precise target. Everyone shares data in near real time through standardized formats, using something called the VO event protocol, a language that lets completely different observatories and instruments talk to each other without human translation. And it works. Since 2017, the network has caught multiple neutron star mergers, black hole collisions, and even a few events so weird they're still being argued over in journals. The response times have dropped from hours to minutes. Some telescopes now trigger automatically when an alert comes through, no human required. The culture has shifted from "let's observe this when we get a chance" to "every second counts, move now." That shift didn't happen by accident. It happened because the community agreed on protocols, shared data openly, practiced drills, and accepted that fast and imperfect was better than slow and polished. Now, contrast that with how we handle near-Earth objects from the solar direction. There is no automatic alert system. There is no agreed protocol for who looks where when something is detected close to the Sun. SOHO catches a comet streaking past, and it might be days or weeks before anyone notices in the archived data. Ground telescopes can't point near the Sun without risking damage. Space telescopes that could observe in ultraviolet or infrared aren't tasked for this kind of rapid follow-up. We have no LIGO equivalent for solar intruders, no network that wakes up and says, "Something just appeared from behind the Sun, all eyes on it now." But we could build one. The technology exists. Solar observatories like SOHO, Stereo, and Parker Solar Probe already watch the Sun, continuously. Ground-based radar can track objects even in daylight if they're close enough. Infrared telescopes can see through the Sun's glare if they're designed for it. What's missing isn't the hardware, it's the coordination, the protocols, the culture of fast response. Imagine if every time SOHO detected a sun-grazing comet brighter than a certain threshold, an automated alert went out. Ground radars in the northern and southern hemispheres would slew to the predicted coordinates. Space-based infrared telescopes would take a quick look. Amateur astronomers with hydrogen alpha solar filters would scan the limb of the Sun. Data would flow into a central clearinghouse, analyzed in real time by both humans and machine learning algorithms trained to spot anomalies. Within an hour, you'd know if that comet was on a collision course or just passing through. Within a day, you'd have its trajectory, composition, and whether it survived perihelion. And if it was big enough to matter, you'd have weeks, maybe months of advance warning instead of days or hours. The gravitational wave network didn't get built overnight. It took decades of infrastructure, funding battles, failed proposals, and a lot of scientists willing to share credit and data in ways that felt uncomfortable. There were failures too. Early detections had false positives. Some events were localized so poorly that optical follow-up found nothing. One event in 2019 initially looked like a neutron star merger, but turned out to be instrumental noise. The community didn't hide these failures. They published them, learned from them, refined the algorithms, and kept going. That's the culture we need for planetary defense. Not perfection, not secrecy, just speed, coordination, and a willingness to be wrong in public if it means catching the next real threat. Because here's the thing. The next object that comes at us from the sun's direction won't send a press release. It won't wait for peer review. It'll just show up, and if we're not watching with every tool we have coordinated and ready, we'll miss it. The gravitational wave community showed us that fast response networks work, that international cooperation is possible, and that the technology to catch rare, unpredictable events already exists. We just have to choose to build it, and if we don't, the question isn't whether something will catch us off guard. It's when, and whether we'll have the infrastructure in place to do anything about it when it does. Part 15. News. 5. James Webb. Space Telescope catches a star about to explode. The power of surprise and timely instruments. In early 2025, the James Webb Space Telescope pointed its infrared eye at a red supergiant star 2,000 light-years away and saw something extraordinary. The star, catalogued as WHG 64 in the Large Magellanic Cloud, was dumping mass into space at a furious rate, shedding its outer layers in vast plumes of gas that glowed in the infrared like a dying ember. Astronomers had seen this kind of behavior before in stars approaching supernova, but never with this level of detail. James Webb Space Telescope's instruments caught the turbulence in the star's atmosphere, the asymmetric eruptions, the dusty cocoon forming around it. 6 weeks later, the star exploded. It became a supernova, a blast so bright it briefly outshone the entire galaxy it lived in. And for the first time in human history, we had detailed observations of a star in the weeks immediately before it died. Nobody planned this. The observations weren't part of a supernova prediction program. James Webb Space Telescope was studying the star as part of a broader survey of evolved massive stars, trying to understand their late-stage evolution. The fact that it caught a pre-supernova star was pure luck, a cosmic alignment of timing, instrument capability, and scientific curiosity. But it was the kind of luck you only get when you've built instruments sensitive enough to see the unexpected, and when you're watching often enough that rare events become probable. That's the paradox of discovery. The more you look, the more you find, and the better your tools, the more you see in what you find. Now ask yourself this question. If we can invest billions of dollars to watch a star explode 2,000 light-years away, why aren't we watching the space between Earth and the Sun with the same intensity? James Webb Space Telescope cost $10 billion and took 30 years to build. It's one of humanity's greatest scientific achievements, a telescope so powerful it can see galaxies forming in the infant universe, exoplanet atmospheres, and dying stars in exquisite detail. But it can't warn us about a comet coming from the Sun's direction. It wasn't designed for that. None of our most powerful telescopes were. We've optimized for the distant and exotic, and in doing so, we've neglected the near and potentially dangerous. The supernova that James Webb Space Telescope caught wasn't threatening Earth. It was 2,000 light-years away, far enough that even its most energetic radiation posed no danger. But the principle matters. Rare events become observable when you have the right instruments watching at the right time. Supernovae in nearby galaxies happen maybe once or twice a century per galaxy, sometimes less. We've only caught a handful in the act of exploding, and almost none with detailed pre-explosion data, but James Webb Space Telescope, by sheer sensitivity and happenstance, saw one. That's what good instruments do. They turn improbable observations into routine discoveries. They make the invisible visible. And if we applied that same philosophy to planetary defense, we'd stop treating near-Sun objects as an afterthought and start treating them as the surveillance gap they are. Here's what that might look like. Imagine a constellation of small satellites, each about the size of a washing machine parked in orbits that give them a clear view of the space between Earth and the Sun. They're equipped with ultraviolet and infrared cameras, designed to spot the hydrogen glow of comet outgassing and the thermal signature of rocky asteroids heated by the Sun. They're cheap by space mission standards, maybe $20 million each, built with commercial off-the-shelf parts and launched as rideshare payloads. You put up 10 of them, spread across different orbits, and suddenly you've got all sky coverage of the solar blind spot. No single satellite sees everything, but together they create a net that's hard to slip through. Every object brighter than a certain threshold gets flagged automatically. Machine learning algorithms filter out known comets, satellites, and instrumental noise. Anything new gets a higher priority and triggers follow-up observations from ground-based radar and optical telescopes. This isn't science fiction. The technology exists right now. CubeSats with ultraviolet cameras have been launched for aurora research and exoplanet studies. Infrared sensors fly on weather satellites and missile warning systems. The only thing missing is someone willing to fund it and the institutional will to make planetary defense a priority rather than a footnote in NASA's budget. We spend more money on a single superhero movie than it would cost to deploy a surveillance network that could catch the next sun-grazing intruder before it gets close. That should bother you. It bothers me. Because when the next one shows up, and it will, the question isn't going to be whether we could have built the system. It's going to be why we didn't. Let's get emotional for a second. We live in a universe that is mostly empty, cold, and indifferent. The distances between stars are so vast that if you scaled the sun down to the size of a basketball, the nearest star would be another basketball 6,000 kilometers away. In that emptiness, Earth is a fluke, a tiny bubble of warmth and complexity that exists only because we orbit at the right distance from a stable star. Life here is an accident, a chemical reaction that got lucky and kept going for 4 billion years. And for almost all of that time, life on Earth has been at the mercy of rocks falling from space. Dinosaurs didn't build telescopes. They didn't have warning systems. They just went extinct when a 10-kilometer asteroid hit the Yucatan 66 million years ago. We have telescopes. We have warning systems. We have the ability to see threats coming and, in theory, to do something about them, but only if we're actually looking. The James Webb Space Telescope supernova observation is a reminder that the universe rewards preparation. Luck favours the instrument that's turned on and pointing in the right direction. We got lucky with WHG 64. We didn't get lucky with 3i Atlas because we weren't watching when it mattered. And the next interstellar visitor, or the next sun-grazing comet or the next dark asteroid from the solar direction, won't wait for us to get our act together. It'll just show up. And if we're still relying on serendipity and after-the-fact analysis of archival data, we'll miss it. Again. So here's the call to arms. Demand that space agencies treat the solar blind spot as a first-tier problem, not a curiosity. Support missions that prioritize near-sun surveillance, even if they're not as glamorous as hunting for exoplanets or mapping distant galaxies. Volunteer to help analyze data from existing solar observatories like SOHO, where thousands of comets sit unnoticed in archived images because there aren't enough eyes to check them all. Subscribe to alert networks that track near-Earth objects and make noise when they update. Write to your representatives and ask why planetary defense gets a fraction of a % of NASA's budget when the consequences of failure are existential. Make this a public priority because right now it's not. And it should be. 3i Atlas isn't coming for us. It probably never posed any real threat. But it exposed a failure in our defences, a gap in our vigilance that's wider than anyone wants to admit. The real invisible visitors are the ones we're not watching for, the ones that come from directions we've decided aren't worth monitoring, the ones we'll only see after they've already passed, if we see them at all. We've built telescopes that can watch stars die across the universe. We've built detectors that can feel space-time ripple from collisions a billion light-years away. We can do this. We can watch our own backyard with the same intensity. We just have to choose to. And if we don't, then the next headline won't be about a comet that missed us. It'll be about the one that didn't. And by then, it'll be too late to build the system that could have warned us. The universe doesn't give second chances. It just keeps throwing rocks. And it's our job to be ready when the next one comes.